This is the 2013 Nissan Leaf. It's an all-electric vehicle. No gas, no oil changes. Literally no maintenance, plug-and-play driving. No more gas station stops, no emissions, no greenhouse gases. The only maintenance required is tires and brakes. Plus I have to wash it once in a while. Let's go for a drive. The first thing you notice in an EV is the total lack of engine noise. It doesn't idle, so there's no vibration from an engine. Acceleration is instantaneous because it doesn't need to wait for revs to generate horsepower. Power is always available. But where's the power coming from? And how is it stored? And how is it delivered? It's kind of like this. The lithium atom loves to lose electrons, so it has a high potential to oxidize and send its lone valence electron into a system. If you give the electron a circuit follow, it will do so, creating a voltage of almost 4 volts. For a battery, this is a very high electric potential. The lithium-ion battery was first developed in the 1980s by John Goodenough and Akita Yoshino, who were later awarded the Nobel Prize in Chemistry. The lithium-ion battery laid the foundation for a wireless and fossil fuel-free society. Lithium has even been referred to as white gold. The Leaf's power consists of 48 modules, each of which contains 4 3.75 volt batteries. The 4 batteries consist of 2 pairs in parallel, then those are connected in series for a total of 7.5 volts per module. Each cell can produce a current of 32.5 amp hours. If we use the formula that power equals current times voltage, then we have a total of 122 watt hours, or 488 watt hours per module. With 48 modules, that results in a total voltage of 360 volts, and a total power supply of 23,424 watt hours, or simply 24 kilowatt hours. You can see here that the electric motor that drives the wheels is currently using approximately 20 kilowatts of power, while the climate control and other systems are consuming about 1 kilowatt. If at that rate, the car could continue on for about 1 hour of driving. That's 21 kilowatts for 1 hour, or a total of 21 kilowatt hours. Remember, the battery is a 24 kilowatt battery. On average, the car will travel 6.2 kilometers per kilowatt hour. 24 times 6.2 equals 148 kilometers per charge. And this will vary depending on how I drive. For instance, notice here that as I go down the hill, the electric motor becomes a battery charger, and the charge is replenished. You can see this here as the graph indicates the car can get 10 kilometers per kilowatt hour while decelerating, but under hard acceleration, all 80 kilowatts of the motor are used and the charge will drop quickly. Notice that under hard acceleration it goes down to around 1 kilometer per kilowatt hour, and while decelerating it goes back to 10. Climate control and accessories will affect the range marginally. Notice that when turned off, the range does extend by a few kilometers. When the 80 kilowatt motor is not being used, the car can sit with the heater on along with heated seats and steering wheel for quite a long time. Sitting in a traffic jam is not a worry, as some people think. The battery pack can get quite warm, but Nissan uses a radiator-style cooling system to carry the excess heat away. The car uses a lithium manganese oxide cathode, which has good thermal tolerance and longevity. The battery will maintain its full capacity for at least 10 years, after which it can be used for energy storage for non-mobile purposes. For instance, storage for electricity generated by solar and wind.